Now that we've spent a lot of time talking about sine and cosine functions and their transformations, it's now time to start modeling real-world data with sinusoidal functions. There are several applications in the real world that have sinusoidal functions or have some sort of periodic behavior, such as the rise and fall of the tides, or the number of daylight hours or darkness hours, and the average monthly temperature. These are things that we know every year at a certain time of year. The temperature is about a certain level. In example 1, it says the table contains the times that the sun rises and sets on the 15th of every month in Center City. And so what I've done for you to help you out is for example, for the month of January, the sun rises at approximately 7:15 a.m. It sets at 5:55 p.m. So the amount of sunlight hours is about 10.67 hours. What we did to find the amount of sunlight in hours was we found out how many hours and minutes had passed, and then we changed the minutes into a decimal number of hours by dividing by 60. What we're going to do is we're going to use this data for the entire year to write a sinusoidal function that models the number of daylight hours for Center City. Now, we're going to call, January is not a variable, right? So we're going to call t equals 1 January 15th. Therefore, t equals 2 is going to be February 15th, t equals 3 is March 15th, and so on. To write our equation, we're going to write something of the form either y equals a sine k theta minus c plus h, or we're going to write one with cosine. Let's start with the two easiest things to find, which are the amplitude and the vertical shift. The amplitude is the biggest number minus the smallest number divided by 2. The vertical shift is going to be found in a similar fashion. The vertical shift is going to be the biggest number plus the smallest number divided by 2. So the first thing I have to do is I have to look at this list and determine which value is the biggest and which is the smallest. Now, we're not actually using these two columns. We've already converted for you the number of hours of sunlight approximately for each month. So it looks like just by scanning through that 13.88 is the max, and that occurs in June, which makes sense for the northern hemisphere that the longest amount of sunlight hours would be in June. And it looks like the minimum here in December is 10.53, which again makes sense because the shortest day of the year occurs in December. So let's find the amplitude and the vertical shift. So for the amplitude, I'm going to get rid of this for a minute. It's going to be 13.88 minus 10.53 divided by 2. So that's going to be 3.35 divided by 2, which is going to give me about 1.675. So there's my amplitude, so I know to plug in for A. The next thing we're going to find is the vertical shift, and like I said, the vertical shift is going to be the max plus the min divided by 2. So 13.88 plus 10.53 divided by 2 is going to give me 24.41 divided by 2 is going to give me about 12.2 0.205. So there's my vertical shift. So I know 2 of my values from the equation. Now what I haven't determined yet is I haven't determined if this is really a sine or a cosine function. So if you think about graphing them, remember here the max is at about 13.8 and the minimum's at 10.53. So look up here at the top at January. Does this look like it's starting on the midline, or does it look like it starts at the maximum or minimum? Well, it looks to me like it starts near its minimum because 10.53 is close to 10.67. That's important because that's telling me to write a cosine function. And more specifically, if it's starting at its minimum, then the equation is probably y equals negative 1.675 cosine of k theta minus c plus 12.205. All right, so we're halfway there. Remember, when we are finding the information to plug into an equation, there's 4 pieces of information. We always start by finding the easiest stuff, which is always the amplitude and vertical shift. And now we're going to do the stuff that's going to take us a little bit more work. And so specifically, the next thing we're going to find is K. So the question is, what's the period? Since we're given information in this table for 12 months, then our period is going to be 12 months. So if my period is 12 months, in order to find K, I'm going to have to set 12 equal to 2 pi over K, and then solve that proportion. So I get 12K is equal to 2 pi. Divide by 12, and K is going to equal, well, 2 over 12 reduces to 1 over 6, so it's pi over 6. We usually leave it in terms of pi. The other thing that I'm going to change here is instead of theta, which is what we were using before, we're going to change that input to t. The reason is because months is a unit of time, rather than theta, which normally represents an angle. So now we've got 3 of the 4 pieces of information. The only thing we haven't dealt with yet is, well, what's the phase shift? Here's what we're going to do to find C, which is a little bit different from what we did in the last section. We're going to take one of the ordered pairs from this table, and I'm just going to pick this ordered pair. Remember, January is month 1. So the ordered pair is 1, 10.67. So when t equals 1, y equals 10.67. We're going to plug those 2 pieces of information into our equation and then solve the equation for C. So 10.67 is equal to negative 1.675 cosine of pi over 6 times 1 minus C plus 12.205. So in order to solve this, the first thing I'm going to do is look for anything that I can add or subtract from both sides. Hey, look, I can subtract 12.205. And I get negative 1.535 is equal to negative 1.675 cosine of pi over 6 minus C. Then I look for anything I can multiply or divide. I can divide by negative 1.675. So this goes away. And I'm left with approximately 0.9164. Now, in order to get C out of those parentheses, I've got a cosine in front of it. We solve by doing the inverse of cosine to the other side. We've done this before. The only thing you need to make sure is that you're in the right mode. So make sure you're in radian mode before you do this. And you're going to get about 0.4118. And that's going to be pi over 6 minus c. So then I'm going to subtract pi over 6 from 0.4116, or sorry, 8. And it's okay to work in decimals. So 0.4118 divided minus pi over 6 is going to give me approximately negative 0.1118, and that's going to equal negative c, and then those negatives end up canceling, and I find out that c is 0.1118. So now we're going to go back up here, and we're going to replace c with 0.1118. This equation represents loosely the number of daylight hours for Center City for any month of the year. What we did was we started by finding the amplitude. The amplitude is the maximum minus the minimum divided by 2. And then we found the vertical shift, which was the maximum plus the minimum divided by 2. Those were the easiest things to find. After that, we determined if we were dealing with a sine or a cosine function. So we looked back at the very first ordered pair, or piece of information in the table. In January, we started at about 10.67. Well, it turned out that was close to the minimum. So therefore, if we're starting at a minimum, it's a cosine function. The period is 12 months because the table is given in months. So you set 12 equal to 2 pi over k and solve for k. We got pi over 6. It was the last step of the problem that was most difficult because we had to do a lot of work. In order to find the phase shift, you take any ordered pair from the table, preferably the first one, and you plug it in for t and y. And then you solve that equation for c. All it is regular old algebraic manipulation. The only thing you need to remember to do is in order to get rid of a cosine on one side of an equation, you have to do an inverse cosine on the other. So there is a part B to this problem, and part B asks you to find the average monthly temperature on May 31st. Now remember that this table represented the 15th of each month. So this is really May 15th. So we would normally call this 5 because that would be month 5, and we wanted to find the average temperature on May 31st. Isn't that a half a month later? So maybe we would plug in 5.5 for t. So we're going to do y is equal to negative 1.675 cosine of pi over 6 times 5.5 minus 0.1118 plus, 12.205. And again, you just need to be in radians to do this on your calculator, and you actually just plug it in verbatim in one full swoop and then hit enter. And if I said average monthly temperature, now that I'm thinking about it, I didn't mean that. I meant average number of daylight hours. So you should get about 13.76 average hours of daylight in May. Now let's go back up to the table and see if that seems to make sense. On May 15th, the average number of daylight hours was 13.42. And in June, it's 13.88. So does it make sense that 13.76 seems to come between those two? It does to me, and it should to you too. Let's do another application problem. Although any sinusoidal function can be written as a sine or cosine function, there will be a difference in the phase shift. For the best accuracy, If the function looks like it is near 0 at x equals 0, use sine. If it looks like it's at a maximum or minimum at x equals 0, use cosine. That's what we did in the last problem, where we determined that our first value seemed to start at a minimum. And that's why I used cosine, and I made the amplitude negative in the equation. So, example 2. The tide in a coastal city peaks every 11.6 hours. That's your period. The tide ranges from 3.9 meters to 3.3 meters. Oh, this is your max and your min. Suppose that the low tide is a t equals 0, where t is the time in hours. Write a function that models the tide, the height of the tide. So first of all, if we start at t equals 0, and that's where low tide is, we would probably use negative cosine because it's starting at its minimum. All right, so in order to write our equation, there are a couple things we need to find. Let's start with the amplitude. Remember, the amplitude is the max minus the min over 2. 0.6 divided by 2 is 0.3. And then the vertical shift is the max plus the min divided by 2. 7.2 divided by 2, and that's going to give me 3.6. So I know two of the pieces of information. So I'm going to start with y equals negative 0.3 cosine of k theta minus c plus 3.6. Remember, we're starting at low tide. All right, so in order for there to be a phase shift, either I have to tell you there's a phase shift, or I have to give you a table of data so that you can find it. And in this particular problem, we did not give you a table of data. We just gave you some information. So if you don't have a table of data, we're not going to have a phase shift, which is nice because then I don't have to worry about it. The only other thing I need to worry about is what's k. In order to find k, they have to tell me the period, which they did. They told me that the coastal city, the tide in coastal city peaks every 11.6 hours. So that means that the period is 11.6 hours, and we're going to set that equal to 2 pi over k, and that's just a proportion, so we're going to cross multiply. So 11.6 k equals 2 pi, and then divide by 11.6, and we're going to get k is 2 pi over 11.6. So now I'm going to go in here, and I'm going to call this 2 pi over 11.6, and we're going to call it t because that's going to be our input variable. So there's my equation. Then in part B, it asks me to determine the height of the tide at 6.2 hours. Again, as long as you're in radian mode, you should be fine just plugging in 6.2. So negative 0.3 cosine of 2 pi over 11.6 times 6.2, sorry, plus 3.6. And then my calculator spits out approximately 3.89, and it's in meters because my other answers were in meters. Another example of sinusoidal functions is the predator-prey situation. The predator-prey situation is, for example, let's say you have wolves, they like to eat rabbits. So the wolves eat the rabbits, and when they eat the rabbits, the population of rabbits goes down. But if the population of rabbits goes down far enough, then the wolves have nothing to eat, and they start to starve. So instead of their population going up because they're healthy and happy and not hungry, all of a sudden they're hungry and they don't have any food, so their population begins to die off. Well, while the wolf population is dying off, they're not eating as many of the rabbits, and so the rabbits have some time to repopulate. And so what happens is the population of the predators and prey just keep going up and down periodically. So, in predator-prey situations, the number of animals in each category tends to vary periodically. A certain region has pumas as predators and deer as prey. The number of pumas varies with time according to the function p equals 500 plus 200 sine of 0.4t minus 2. And the number of deer varies according to the function d equals 1500 plus 400 sine of 0.4t with time t in years. Use the functions to determine how many pumas and deer there will be in the region in 15 years. This is a very simplistic problem because all you have to do is plug in 15 for t. So in the puma model, when you plug in 15 for t, and I would plug it, when you plug it in the calculator and you plug in sine, it gives you an open parentheses. I would do another parentheses for this. You're going to find out that the number of pumas is going to be about 323. Notice that I did not say 323.3. When you're talking about population, and we discussed this with exponential and logarithmic functions, you cannot have a decimal number of people or animals or objects. So make sure you round to the nearest integer. The deer population is 1,500 plus 400 sine of 0.4 times 15. And again, when I round that off to the nearest integer, it's going to be about 1,388. The other thing that I want to mention about this is it is very easy to find the max and the min, what the populations fluctuate between. Remember, this is the amplitude for each equation. And this is the vertical shift. Remember, I said sometimes I like to trick you and stick the vertical shift in front of the function instead of behind it. So the maximum is going to be the amplitude plus the vertical shift. I should say vertical shift plus amplitude. So for the puma population, the highest it's going to get to is 700. And the lowest it's going to get to is the vertical shift minus the amplitude, which is 300. So the puma population will always fluctuate between 700 and 300 pumas. The deer population is going to fluctuate between 1,900, because that's 1,500 plus 400, and 1,100, because that's 1,500 minus 400. And those are some real-world sinusoidal functions modeled for you.